Today we'll be discussing a technique called finite element analysis that allows us to break down very complex differential equations that govern either fluid flow, heat flow, mass flow, or other flows into discrete elements and allows us to run those computations on the university's supercomputer. As part of this, we'll be going over some of the background on what finite element analysis is. It's also called finite element modeling, why we'll be using this in this course, and then we get into a little bit more in depth on how a computer creates the geometry that we'll need in order to create our simulations. And then we'll switch over to the program we'll be using for finite elements called ANSYS to go over the homework for next week. Finite element analysis is a technique we'll use to translate the complex partial differential equations that govern things like fluid flow with Bernoulli's equation. We'd look at heat flow equations, mass flow, radiation, and like breakdown of nuclear materials. These are all governed by these complex differential equations that can only be solved if your geometry is very, very simple. When we get into complex geometry, like we see here with biological specimens, we'll have to break that down into little volumetric elements, and it calculates each of those quantities on a volume by volume basis. There's a very famous example here of a cow versus a Jeep. These were two separate studies looking at first, the aerodynamics of vehicles is very important in terms of fuel mileage and economy, and Jeeps being very squarish like that are notoriously bad at gas mileage. Then we also see a cow. The cow simulation was done in order to show the kinds of wind speeds that are necessary in a tornado to lift a cow off the ground. And we find that the cow is actually the more aerodynamic of these two. So how do we get started with this? As you see here, this is the Navier-Stokes equation, which governs how fluid flows based upon velocities and pressures. You see it's a mixed like partial differential equations with we've got first order terms on the left-hand side, some second order terms on the right-hand side. This is a difficult problem to solve by hand, and so we'll simplify this and then allow the computer to solve it for us millions of times a second. The first step in this process is to break down our geometry of the object that we're looking at into faces, like we see here with the Utah teapot. This object was the very first thing to be rendered completely in 3D on a computer by a man named Martin Newell, who's worked on it as a PhD project here at the U in the 70s. He, alongside John Warnock, whose name might sound familiar based off of the building on campus, went on to found Adobe Systems. So you can see here that our three-dimensional object has been transformed into a series of two-dimensional faces. So this right here would just be considered one face. And we're considering this a two-dimensional object for the moment because we're only looking at the very surface of this. There's no definition on what is inside or outside of this object, but we then can extend that out from these faces into volumetric elements like cubes in order to create three-dimensional meshes. A lot of the geometry that we'll be dealing with when we first import it into ANSYS starts out as just these two-dimensional faces, usually either a square or oftentimes with the STL files, they're defined always as triangles. When we import that stuff into ANSYS, we then want to convert all of this over to volumetric elements. So we effectively turn these into cubes, and these cubes then form the basis of our cells, is what we call them in the simulation, where each volume element will have temperature and pressure and velocity data associated with it. And we build out these surface two-dimensional files. We fill them with a bunch of these 3D cubes, and that becomes the starting point for our simulations. As an example, here's a iguana lung that we are currently working on in the lab. On the left-hand side, you can see the exterior surface of the lung. It might be a little bit hard to make out, but each of these spots on the lung is a little face, just like we saw in the Utah teapot, just happens to be much finer resolution. Now, if we were able to cut this lung to look at the interior, that's what we see on the right-hand side. You see the very center of the lung itself is a little bit of a coarser mesh. It's just more regular, larger cubes. And then as you get closer to the surface here, you see that these volume elements are much finer, and we'll discuss the reasons for that a little bit later on. Here we see a real-world example of finite element analysis. On the left-hand side, you're looking at a two-dimensional mesh of first a copper wire here in gold, as well as something we call a choke or an inductor here that prevents magnetic fields from passing through it. Usually this is a piece of just iron, and then air that's surrounding it. So you see that when we've got surfaces that are close together, or two different kinds of surfaces that touch, we want a much finer mesh because those interactions are going to be much more complicated. Whereas out here in just the medium of air, we have a relatively coarse mesh because those lines should be nice and straight. We see that the visualization, the result of this is that we see these magnetic field lines traveling through that are always going to be perpendicular to the flow of current through a wire. And you see how this choke or inductor guides these field lines alongside of it, such that on the interior we get no change in those directions. As an aside, this same kind of iron core is used in a lot of equipment that's connected to AC power. The laptops that you've got have it. You'll have this square adapter that plugs into the laptop itself that comes out to a cable, and you have a cylindrical something called a choke, which filters out this 60 hertz signal, which is what all the power operates on in the US. If these kinds of adapters weren't here, sometimes with audio signals you would hear a low hum, and that's often the 60 hertz signal coming from the power line. Just kind of an interesting thing to note. Before we get into the math behind finite elements, I'd like to give you a couple of examples of how we would use this and how we would model this in biology. This is something called a counter-current heat exchanger. We also use this in a lot of industrial processes, power plants and power generation, looking at boilers that all use this kind of technique, where we would have one hot stream of a fluid going one way and a cold stream going the opposite way. The trick is that we want to pull heat from the hot stream into a cold stream. At the top here, this is the inefficient method where the arteries and the veins are separated in the extremities. We do see that our extremities here retain a much higher temperature in relation to the air than with our true countercurrent exchanger. But in our top case here, the majority of this heat is lost to the surroundings, which is going to be very calorically inefficient for the animal. This return blood flow to the heart, then has to be heated up again. It's going to cause possible hypothermia in the animal. It's really, bad for a warm-blooded animal like this. But if we go where our arteries and veins are very close to each other, we're losing more heat as that blood flows to the extremities, but a lot of that heat gets directly put back in this return venous flow. So our extremities end up being colder, but we're losing less heat to the outside environment. And in these Arctic conditions, you really want to try and retain that body heat as well as you possibly can. We see the same thing in birds as well, where this is a little bit more extreme of a temperature difference. I could get down almost to freezing, but still, we can try and transfer the heat from the artery to the vein, just so when we get that return blood flow, we don't have to heat it up as much, and we don't lower the core temperature of the animal as much. Now let's take a look at how we would transform these partial differential equations into a form that the computer can understand and use. And let's go through the process by hand of what the computer is doing to calculate our end results. So here we'll look at a one-dimensional example of heat transfer. Think of this as just a long wire that has an infinitely small thickness, so we don't have to worry about heat spreading transversely, so like this direction or this direction. Our heat is only going left and right in what we'll call the x direction. So we can take our three-dimensional equation for heat transfer, and we can simplify this quite a bit. So in our case, we have no change in y, we have no change in z, and our q term here, which would be energy that's generated within it, we'll set that to 0, so that cancels out. So we really just have these two terms, which what this really means is the change in temperature with the change of position in x, and K is our thermal conductivity of our wire, and that's going to be equal to density with the specific heat, and our change in temperature with change in time. So we've greatly simplified that equation, but in addition to that, we'll also need to provide some extra parameters for the simulation, and that's our boundary and initial conditions. So our boundaries will say that there's a fixed temperature. On the left-hand side, I had that at 100 degrees, and on the right-hand side, 0. And then within the wire itself, we're saying that initially everything's going to start at 0 degrees. Now that we've simplified our equation and given initial and boundary conditions, our equation for heat transfer looks much simpler. Let's go through these terms one by one. So you see here, we're trying to solve for U sub j at n+1. Our U is our temperature. The j is at our current position, so this would be right here if we're going to solve for this element. And our n is our current time step. So obviously we're trying to solve for n+1, which is the next time step over. In the equation itself, we have a k value, which is our time step that we step through one by one. We'll use 1/10 of a second here. Our h value is the width of our element that we want to analyze, because this is 10 meters in total, and I've got 10 elements. H equals 1 meter, so it should be relatively easy. We have an R value, which is just defined as K over H squared to make things simple. That means that our R value is 0.1, or 0.1 over 1 squared. So let's try and step through these one at a time to figure out how we get from our current time step to our next time step in that element. Let's solve for this element right here, J. We know that U, which is our temperature of J at n plus 1, which will be the next time step, is equal to 1 minus 2 times 0.1, since that's our R value here, times U sub nj. So this is our temperature right here at our current time, which is 0. That should simplify out nicely. Plus 0.1 times this U of j minus 1. Our j minus 1 here is that left-hand boundary. So that's fixed at 100 degrees. So we've got 100. And then plus 0.1 times this element here, which is j plus 1, which is going to be 0. So we find that this simplifies out such that U of j n plus 1 is then going to be equal to 10 degrees. It's just from this term right here. That was our first time step, and we only had to calculate that one element, this spot right here, because there was only one non-zero element in this simulation, this fixed boundary at 100 degrees. So now let's take a look at our second time step. We'll have to do that for this element here, U, and that will give us another, plus 8 degrees when everything gets simplified. But then we'll also have to do it for this element here as a U, where this U of j n plus 1 is going to be equal to 1 minus 0.2 from that. And we've got the 0 here because it's currently 0, plus 0.1 times this term here, our j minus 1, which is going to be this element now. So that's 10 degrees. And then plus 0.1 times, this will be j plus 1 right here. And again, that's 0. So then this simplifies out to being, since that term is 0 and that one's 0, to being 1 degree. So we'll have 1 degree here and 18 degrees here. And we'll have to just continuously step through the simulation, and it will slowly show that the heat will transfer throughout this wire until we get to a steady state. So we see here we've got 18 degrees and then 1 degree. Again, now this time around we'll have to go through and analyze 3 different elements to add to the next step. That gets us to this solution, and then this, and it will slowly move across the wire depending on the time step we've chosen. Eventually, when we go through enough time steps, we'll arrive at this solution that won't change no matter how many more time steps we go through, because we still have fixed boundaries that aren't going to change in time. We've got no generation within the media. So it'll come to a steady state is what we call it. You'll notice these numbers are very round, looks really easy to deal with. And that's because if we plot this just on a chart where our position here is our x and our temperature is our y, you'll see that this will be a linear line going from x equals 0 to x equals 10 meters. And you'll find this a lot with very simple simulations, that they'll arrive at a steady state solution. It's not going to change in time. Now, when we deal with more complex airflow and fluid flow, we'll end up usually getting some oscillating patterns and some more complex patterns because we've got much more complex geometry. And that is a very simple one-dimensional example of how a computer is going to translate these differential equations into algebra to determine these complex fluid flow, complex heat flow simulations. We're doing this just in one dimension, but the computer will translate this out to 3 dimensions, where we've got something like maybe 10 million different cubes that we're dealing with at any given time step, where it has to calculate the say pressure and velocity of a fluid at every one of those cells simultaneously. So in order to do that, we're going to log into the university's supercomputing cluster, and we're going to throw just a lot of computer resources at this problem. In order to create our simulations, we'll be using a suite of software from ANSYS. Primarily, we'll use a program called ANSYS Workbench, which acts as a front end for all of the other subprograms and solvers that are included within it. Primarily, we'll use one called Fluent. So we'll start a new fluid flow simulation with that program. We'll need to use a program called Design Modeler to create our geometry. So we're going to start out with a very simple two-dimensional box for this one. After we kind of create that geometry, then we need to set what our boundaries are. So we'll have a wall here. We'll have fluid flowing in from this side, fluid flowing out from this side. And the top here, we're actually saying there's fluid flowing in, but from this direction. Just means that we won't get any fluid going up through this top of the wall. And we'll go into that a little bit later on why the reasons are for behind that. Then we also need to create a mesh with these sets of geometry. So that is involved in splitting out the geometry here into much smaller sections. So that we can compute those values as they change from one box to the next. Then we'll need to set what our actual conditions are here. So this in terms of our fluid velocity going in, fluid pressure going out, and what initially our conditions are for this whole geometry. Then we'll actually run the simulation, see how that begins to converge and finalize on a one correct answer, and then we'll analyze those results in a separate program called CFDPost.